Okie dokie. Today we're gonna learn um, how to make a proton with 3 electron strings. I had 3 titles for this lecture. I'll probably post it as Heisenberg's relativistic uncertainty principle. And we'll see why in just a second, because we're going to be starting with Heisenberg's uncertainty principle right here. The change in momentum times the change in position is greater than or equal to h bar over 2. And we're going to make it relativistic by making the momentum, of course, is mv. We'll do the change in position as the radius of our string, electron string. And of course, the mass, since we're going to be doing a relativistic particle or string moving, rotating, orbiting, whatever you want to call it, we're going to have the mass be relativistic. So we'll use Einstein's mass relativity equation, which is m0 over the square root of 1 minus velocity squared over the speed of light squared. So all that stuff is right here, and it's greater than or equal to h bar over 2. Let's go ahead and fit everybody in here. We are going to do an electron, so this will be the rest mass of the electron, me. I'm going to change the velocity to beta. Beta is v over c. So if this is v, then beta times c is v. So v is the beta and the c. The r is right there, and v over c is beta right there. And h bar, of course, is equal to h bar is equal to h over 2 pi, and then the 2 down the denominator will turn it into h over 4 pi. So this is this. I just wanted to break it down so we could have the r constants here. So this is our equation. We'll be solving for beta here. We know the mass of the electron. We know the speed of light. We know Planck's constant here. So the only thing we leave to suppose on is the radius or the size of our relativistic electron. I'm going to make it about a third of the size of a proton, which is a proton's about 1.2 times 10 to the minus 15. And I know I always choose these numbers, and a lot of people might complain that, hey, you're choosing numbers to make stuff fit, but it doesn't matter whether I use 3.15 or 3.2 or 3.4, whatever. It's going to make it a little bit off, but it's not going to change that much the answer. So this is not, all the numbers that I choose when I choose a number is not outlandishly ridiculous. You know, a third of the proton's size is about 3 times 10 to the minus 16. So I'm just choosing this as just to wow you with how close we can get with the numbers by making a fairly respectable guess for the radius of our relativistic electron string. Okay, so if we know all these people, we plug them into this equation, and you can do the algebra or have a calculator or Wolfram Alpha or something, solve for beta. And if you solve for beta, you will get 0.598665504. A lot of people might complain, hey, what about your significant figures? Well, yes, it's true. Here we only have 3 significant figures, maybe 1 here, and so on, and 4. And how can we steal 7? We don't really need all 7 of these. We need about maybe 6 of them to get an answer that's fairly reasonable. But here we have to get it because of the form of the function of the beta function, so we will have to take quite a few more numbers. But this is not an outrageous beta to come out of here using this. So if we used more accurate numbers for each of these things, we would still get very close to this beta, which of course is the velocity divided by the speed of light, which I've mentioned before, and I assume you're probably familiar with. We're going to figure out if an electron had this beta, what would be its total energy. So here's our relativistic energy equation for total energy. Mass of the rest mass of the electron c squared square root of 1 minus beta squared. And when you type all that in, the mass of the electron in here, and the speed of light, 3 times 10 to the 8th, and you take this beta and plug it in here, and then you'll also have to divide by the charge on an electron, just to get the electron volts out of this thing. And when you do when you figure it out, this will come out to be 313 MeV, mega electron volts. When you figure out this changes from joules to mega electron volts. You'll have to divide by the charge of the electron, which is charge on the electron is about 1.6 times 10 to the minus 19th coulombs. So if you take this number and divide by this number, and then divide by another 10 to the 6 to get the mega, you will get this. I assume you know all that if you're looking up this lecture. Okay, so we find that the mass of an electron, one electron string that's moving relativistically, according to Heisenberg's uncertainty principle, relativistic uncertainty principle, is about 313 MeV. To make a proton, we'd need, of course, 2 positrons moving at this, and 1 electron squeezed in the middle, orbiting in opposite directions, so the magnetic moments would line up to bind these 3 particles very strongly, so strongly that proton can't be ripped apart except with antiproton. Anyways, if you take 3 of these, of course, we're going to need 3 of these masses. 2 positrons and 1 electron is 3 of these particles. And 3 of these particles will be 3 times 313 MeV, which is about 940 MeV. So I propose that this may be a possible structure of the proton, comprised of 3 electron string rings, moving relativistically, with not too crazy of an idea of the radius, and the radius is actually the only thing that we chose, that we had as a variable. Everything else is constants. So I don't think we can fight very much with the radius of this electron string there. Anyways, so 3 times that is going to be 940. That's our theoretical value for the mass of the proton, according to this analysis. The experimental is about 938.3 MeV, and so you get an error of about 0.2% error, which is not bad in theoretical high energy physics. I hope you enjoyed this lecture, and I look forward to any comments at the bottom. Thank you very much.